epicell or a chondrocyte for MACI are considered adherent cell populations. That means when these cells are put into cell culture, they want to adhere to the plastic, and they're going to form their colonies on the plastic, and they're going to grow and proliferate off these colonies. It is an adherent population similar to the chondrocytes we use for MACI. Where epicell differs is referred to as a xenotransplantation product. So every epicell flask, every epicell culture is co-cultured with a murine feeder layer, a growth-arrested fibroblastic layer that will be pre-coated onto the flask, and then the keratinocytes will be introduced to that feeder layer. Over the course of the culture, the keratinocytes will literally take over the culture, and the murine fibroblast cells that were once adherent will become non-adherent and be washed away during our various feeds and rinse processing. So we run into some different challenges with the amount of surface area physically available to grow the cells. If the cells become over-confluent, meaning they start to grow over on top of each other, that can affect viability, that can affect culture performance. So we have some space limitations, but then in addition, when you want to harvest a full confluent set of cells or cells that are bound to a surface, you have the challenge of basically creating a homogeneous mixture of individual cells so you can get accurate cell counts and things of that nature. If you want to control the gas exchange on our flasks, we will choose flasks that have the appropriate level of filtration, 0.22 micron filters in their caps, and then design or purchase incubators that control that gas flow, that percentage, etc. We'll then control the temperatures in the incubators, put in defined ranges, etc. So it almost becomes using this environment and the equipment to control our process parameters. Unlike a bioreactor where you can really control every single thing for that lot, for that one run, we have to rely on a more grand scale of control. And then our process controls and our SOPs and our procedures that are all part of our process validation, part of process development, part of our process validation moving forward.
The expansion, as any cell culture, require the cells to have nutrients or a culture media available to them. And in this particular case, in the CAR-T space, we use single-use reactors or single-use systems where the cells are contained in those containers, and the media, the culture media, is transferred into those, allowing the cells to have fresh media and to grow in those.
Each type of cell has its own peculiarities, but they're mammalian cells and they have a lot of the same properties that CHO cells have, for example. They double about every 24 hours. They're sensitive to shear, but you can mix them and use a lot of normal bioreactors or equipment to grow these. Also, all of the GMP principles, good documentation, testing, training, everything that you know about operating in a GMP facility applies to these T-cell therapies.
In terms of critical process parameters, temperature is a key one. We don't want to have the temperature too high or too low. That will affect the growth and proliferation of the cells. Also, we have the amount of culture media, the composition of the culture media get in the way of how the cells will grow and proliferate.
So it seems like you could vary a lot of parameters here, and the goal is to end up with a lot of the T cells of interest. So as you're developing this process optimization, what are the knobs that you're turning in developing the correct conditions for your outcome?
Sure. So usually we start with a small scale so that we can kind of explore multiple conditions at once. And so, you know, as long as it's kind of comparable to our at Prodigy scale, then we can glean some information from those kinds of experiments and make sure it's actually relevant before we scale it up. And so some of the things we can look at are, the media components and making sure that this is actually sufficient for our cell use. And so it's also useful to try this process out in various number of donors and patient material, because there is a lot of variability in that starting material. And so making sure that everything that we're changing or everything that we're implementing for our process is actually appropriate for the cells that we're using in the clinic. And so things could be, the media type or the components of it, if we need to supplement it with something, so we can kind of do external kind of measurements to figure out what nutrients are left over, if there's anything being depleted. We can take a look at the different antibody concentrations and seeing how that will affect the activation of the cells, if that will affect the transduction of the cells, and see how that will affect also the expansion as well, and see whether or not, is this too aggressive? Is it not aggressive enough and the cells are not even doubling? And then there's also, what kind of seeding density is appropriate? Is it too much and, they're reaching a certain plateau too early? And there's a lot of different things that we can look at. The cells are the main kind of product. And so a lot of care goes into it, making sure that the cells are really healthy, the viability stays up. It's very different from, like recombinant protein world, where you kind of work the cells into production and you kind of abuse them, and in the end the cells kind of go away and you don't have to worry about it. But for this process, we have to make sure that we're being gentle enough with them and the cells are happy in the end.
Yeah, and the cells are your product. And as you said, each donor is bringing his or her own cells to the table. So every cell is precious and every donor is different.
Right.